So let's start with number 3. We have a proton is moving along the direction of the electric field, and we want to know what's the potential difference. So although you could probably do this by plugging numbers into an equation, I like to always picture what's going on. I'm going to draw my high voltage and my low voltage. The electric field points to that low voltage or low potential. And now I'm going to visualize what it says here. It says that a positive charge is moving along the direction of the field. So that means that my positive charge is moving to the right. And we want to know what is the potential difference between the starting point and the initial points. So we're told that it's moving a distance of 10 centimeters. So that's your delta X, or we also call it D. So this is just a plug and chug where you have the definition of potential difference is equal to negative E times D. That the potential, or really you can think of it that the electric field between 2 points, the amount of the electric field depends on that potential difference between the 2 points. So that's what this equation is saying. So we're just going to plug in -3. This is the field right here. And then the distance, we're going to plug in 0.1 because we convert 10 centimeters to meters. And then we'll get 0.3. So technically the potential difference should be negative because this charge is going towards a lower potential, but that wasn't a choice, so we just have to pick the best answer. So the best answer is that the difference in potential between the 2 points does have a magnitude of 0.3 volts. Number 4. So in this one, what we have is we're going to have an electron, so a negative charge. So it's being accelerated through a potential difference of 5,000 volts. So it's going this way. It's going from a low potential to a high potential. That's why the potential difference is positive. 5,000 volts. And what kinetic energy does it gain? Well, we learned that this charge is going to lose potential energy and gain kinetic energy. So the potential energy that it's going to lose is equal to Q prime delta V, where Q prime is this electron here, which has a charge, Q prime, of negative E. E is this number right here. And so we just plug these numbers in, this 5,000 and negative 1.6 times 10 to negative 19, and we're going to get negative 8 times 10 to negative 16 for the change in potential energy, because it's decreasing, hence a negative number. But the kinetic energy is going to increase because the change in kinetic energy is equal to negative the change in the potential energy. If you lose potential, you're going to gain kinetic. So that's why the answer is positive. Let's do another one here. At what distance from this charge would the potential be this? So this one is more of a plug and chug, where it's not like the ones we've been doing where you have a charge moving from one place to another. Here you just have a charge, and you want to know at what distance R with the potential at this point, let's call this point P, then the potential at point P would be the 4.2 times 10 to the 4. Well, the potential at that point is due to this charge, and the equation that gives us the potential due to just a point charge is kq over r. So we plug in k here, it's just k, same thing, Coulomb's constant, and the charge is q, is 8 microcoulombs. Make sure that micro is 10 to the negative 6, so q is 8 times 10 to the negative 6. And then we're looking for r, but we're given v, or vp, the potential at this point. So we're solving for r, get r by itself, and you'll get kq over v. And then just plug and chug. The purpose of this problem is just to make sure that you know which equation do you use when you're trying to find the potential at a certain point due to that point charge. When you plug in the three numbers, you should get about 1.7 meters.